Very good morning to all my dear students. Today I will be starting with embedded firmware, that is the next part of the communication interface. So till now we have seen what is an embedded system. Fine, I'll just brief about what all we studied till now. So we just imagine that we have an embedded system, what all it contains. Okay, so this embedded system mainly it contains as a microprocessor or the controller. So that is the core of the embedded system. So we studied many core of the embedded system, DSPs, ASICs, PLDs. Okay, so these all will come under the section of core of embedded system. So once we have studied the core, next thing comes is a memory. So memory is again a very important a component of the embedded system. So we studied different types of memories. Then after we need a memory, we need to communicate with the outside world. This embedded system has to connect with the outside world. So to do that, we have to have sensors and the actuators. So that is the next section we studied, which is input and output devices as sensors and actuators. We studied many sensors, many actuators, okay, so which we use it in the embedded system. So some of them you'll already know, and some of us introduced newly into your in your syllabus. Okay, so this is the sensors and the actuators. So once we know all the sensors and actuator, we have to connect this entire embedded system, okay, to the devices. Like if you have to connect any sensor, how do you connect that sensor to this embedded system? So we are depending on the type of the sensor, type of actuators, or whether you connect this embedded system to the PC or the desktop for the simulation. So there are so many things. Okay, so to communicate with the outside world, there are a number of interfaces we have to study, and that we studied in the previous section. So we studied many communication interfaces. One are single wired, one are four wired, some are wireless, and some are wired. So different communication interfaces we have studied till now, along with the other components of the embedded system. Next comes is the on the microcontroller, the processor, we have to dump the program. Okay, and that program have to work with these sensors and the actuators using the ports. Okay, and then process that in the controller and then give the result on the actuators. So there has to be a program running on this processor or the controller, and that program is nothing but called as embedded firmware. Okay, firmware is nothing but the software. It's another name of the software. Fine, so what is this embedded firmware? Embedded firmware refers to the control algorithm or the program instructions and or configuration settings that an embedded system developer dumps into the code memory of the embedded system. So we have to dump that code, the code which we have written into the code memory of the embedded system. It is unavoidable part of the embedded system. We cannot change that. It is unavoidable. It means that we cannot neglect it. So we have to dump the program which has to be run on the processor. There are various methods available for developing the embedded firmware. There are various methods, like we have to write the program in the high level language like C programming, C++, embedded C, using an integrated development tool. Okay, integrated development tool is nothing but the one which you have used, Keel, right? It's a IDE. The IDE will contain what it contains. It contains the editor where you write the program in the lab. It contains a compiler. Obviously, it needs a compiler which converts into a program into machine level language, and then it has a linker. Okay, then debugger, simulator, etc. There is a debugger also, as I had said earlier. Then IDEs are different for different family of the processor and the controller. So suppose ARM uses Keel, Texas Instrument kits also will use Keel. Okay, and they can also be used with the Code Composer Studio. So different platforms or different processor, the controller work with different types of IDE. Okay, for example, Keel Microvision 4 IDE is used for all the family of 8051 microcontroller, since it contains generic 8051 compiler, that is C51. Okay, so this 8051 earlier we had it, even some of your seniors had this controller, that is 8051 controller. Most of the small electronic devices still use this controller. So this 8051, along with this, the editor what we had used is Keel Microvision 4. Now we are using 5. Okay, so then write the program in assembly level language. This is another way, and then using the instruction supported by your application, target processor or the controller. There are two ways of writing. One is either you to write the that is embedded C and embedded C++, or another way is writing the assembly level language, okay, supported by the processor or the controller. Now you have seen some of the instructions of assembly level language are different in microprocessor 8086 and they are different in the ARM controller. So in the Keel software itself, we can either write that is embedded C or C++ as high level language. Also we can write the assembly level language, and that there are two programs for you in the lab to write the assembly level language program in the Keel software. We'll be doing it as a study programs. It's not there to implement, it is done to be as a study program. Okay, so we can also use assembly level language as well as the high level language in the Keel software. The program written in high level language or assembly code should be converted into a processor understandable machine code before loading into the program memory. So this is already you all know. The process of converting a program written in either high level language or processor control specific assembly level language to machine readable binary code is called as hex file creation. So we have seen in the lab, so once you do build what it say, building the hex file. Okay, hex file is nothing but in terms of zeros and ones. So that hex file will be created when you convert an assembly level language or high level language into a machine level language. The methods used for hex file creation is different again depending on the programming techniques used. If the program is written in embedded C or C++ using IDE, the cross compiler included in the IDE converts it into the corresponding processor of the controller understandable hex file. Okay, then if the assembly language based programming technique is used, the utilities supplied by the processor or the control vendors can be used to convert the source code into the hex file. Also, some third party tools are also available which may be free of cost for this conversion. Some of the IDE will already support this, or if they are not supporting, we can use a third party which are free in cost. We can use them to convert the file into an hex file. Okay, so for the beginner in the embedded for software field, it is strongly recommended to use a high level language. Assembly level language programming becomes slightly difficult for the beginners, so we usually go for a high level language based on the development technique. Writing codes in high level language is easy. Okay, the code written in high level language is highly portable. Okay, so when you write embedded C and if you want to like you have dumped on some embedded system and you want to port that means I hope you understood what I mean by port. It is changing the devices. Okay, so when you want to port that, it is highly easy. It is very easy to port the code written in high level language. The same code can be used to run on different processor or controller with little less or small modification. The only thing you need to do is recompile. Okay, once you port that on the other embedded system, you have to just when you are using another processor or another controller with just a small modification, you can use that. Only thing you need to do is the recompile. Okay, when the required processor ID with the required processor's IDE after replacing the including files for that particular processor. The programs written in high level language are not developer dependent. Any skilled programmer can trace out any skill can trace out the functionalities of the program but by just having look at the program. Okay, so it now depends upon only on the developer. Okay, it's not developer dependent. Any user, if they see the program, if they understand the comments, then they can understand the program. It will be much easier if the source code contains the necessary comments and the documentation. Fine, it is very easy to debug, and the overall system development time will be reduced to greater extent. Okay, if you write the high level language programming, it is very easy to debug, and overall system development time also will be reduced to a greater extent. So earlier slide we talked only about the high level language. What are its advantages? It is easy, highly portable, it can be changed by with slight modification, it can be used with any processor or the controller, and they are not the dependent on the developer. Okay, next we go for the assembly level language, wherein embedded software development in assembly level language is tedious and time consuming because it contains lot of instructions. Even for a single instruction, suppose we have a for loop here, the same for loop if we implement in assembly level language, it will become very huge. So it is time consuming and tedious. The developer needs to know about all the instruction sets of the processor, the controller, or at least he should carry an instruction set reference manual with him. A programmer using assembly level language technique writes the program according to his view and taste. Okay, often he may be writing a method or the functionalities which can be achieved through a single instruction as an experienced person point of view by two or three instruction in his own style. So what some person, what they will do, there is a single instruction, but to understand the program or to make it easy or to make it readable, sometimes the programmer can use two instruction instead of the one instruction. So likewise, it depends upon the developer. Fine, often that's what I said. So the program will be highly dependent on the developer. It is very difficult for the second person to understand the code written in assembly level language, even if it is well documented. So even if it is well documented, it is very difficult to understand the program because the program has been written in the way of a programmer. Okay, so he might be using a different instruction. If proper documentation is also done, sometimes it's very difficult to understand the assembly level language code. Okay, so two types of control algorithm design exist in the embedded firmware development. The first type of control algorithm development is known as infinite loop or the super loop based approach. When the control flow runs from top to bottom and then jumps back to the top of the program in a conventional procedure. So this we have already seen in the program. Okay, in the lab program. Now if you want to how you are controlling your program. Okay, either you want to do it continuously or you want to do it at once and stop it. So okay, if you want to do it continuously, you have to put it in an infinite loop. And how to put it in infinite loop, we have already seen. You have to use while one. While one will is an instruction which will execute all the instructions put within this braces. Okay, infinitely. Okay, so there is no end for it. Continuously it will be executing. Only when you stop the execution it will stop it. Fine. The second method deals with splitting the function to be executed into tasks and running this task using a scheduler, which is part of a general purpose or real-time embedded operating system. Okay, first approach is the infinite loop, second approach is the super loop. A second approach is called splitting the function into number of tasks and then executing those tasks on the scheduler basis. So it is not continuous. Okay, whenever we want it we have to execute, but in the earlier case it will execute all the time. So this is the second one which will execute for according to the scheduler, which is a part of the operating system. Next we go for other system components. So once we know the core, memory, sensors and the actuator, communication interfaces, and then the embedded firmware, what software we have to write it on the program and how to write it. Now next section is what are the other system components apart from these, if any, and we will see here in this section. The other system components refer to the components, circuits, ICs which are necessary for the proper functioning of the embedded system. Some of these circuits may be essential for proper functioning of the processor, controller or the firmware execution. Fine. For example, a watchdog timer, it is very important. Fine. Reset IC, brownout protection circuit. These all are different components which are present inside the embedded system. They will help the embedded system, they will protect the embedded system. Fine. How do you protect that? Either in the hardware level or in the software level. Fine. Some of the controllers or SOCs integrate these components within a single IC. Doesn't require such components externally connected to the chip for proper functioning. Okay, what some of the processor, the controller will do is they already have these components built inside them as a chip, so there's no need to use it externally on the embedded hardware. Okay, let us study the first circuit which is used in the embedded system is reset circuit. It is essential to ensure that the device is not operating at a voltage level where the device is not guaranteed to operate during system power on. Okay, we have to take care that some voltage level specification is given to the embedded system. Okay, for example, suppose an embedded system has to work at 15 volts only. Okay, now if that voltage level goes above 15 volt, we have to take care some measures, okay, so that it is not spoiled. Okay, to guarantee that it is not going above 15 volt, we have to use some circuit, and that circuit is called a reset circuit. Fine. The reset signal brings the internal register and the different hardware system of the processor, the controller, to a known state, and the state and starts the firmware execution from the reset vector. Normally the vector address, that is 000 for conventional processor or the controller. Fine. So what it does, it will produce a signal. Reset circuit will produce one signal, and that signal what all it will do, it will bring the internal register and the different hardware system to the reset condition, to a known state. What was earlier before the starting of the processor, whatever was the state, it will bring to that state. Okay, and this is all done by calling a reset vector. What is a reset vector? We have seen in the module 2, right? Module 1, reset vector. Okay, it will start at 000, that is boot code will be executed. Okay, so always sometimes, or maybe you can say in most of the processor, the reset vector will be at 0000. Okay, so the reset signal can be in either active high or active low depending on the processor. So if it is reset bar, suppose there is a microprocessor, okay, a pin of the microprocessor is reset bar. What is the meaning of this reset bar? If you give a low signal to this reset bar pin, it will go into a reset condition. If it is high, suppose if it is only reset pin, not bar, then if you give a signal of high, then the processor is under reset condition. So since the processor operation is synchronized to the clock signal, the reset pulse should be wide enough to give the time for the clock oscillator to stabilize before the internal reset state starts. So here all the processor works on the clock signal. So you know how the clock signal is. Fine. So it may be a positive edge triggered, or maybe it is negative edge triggered. So during the suppose it is a positive edge triggered, the reset signal should be active high or active low depending on the processor within that duration. It means that before the positive edge, the reset signal should be on, and even after the positive edge, it should be on for some time. So it will recognize the reset signal and then starts its operation in the internally. Okay. Reset circuit signal to the processor can be applied at power on through the external passive reset circuit comprising a capacitor, a resistor, or through a standard reset IC like Max 810 from Maxim Delars. So there is externally there will be one circuit. That circuit will give you the reset signal to the processor or the controller, and that circuit will either contain a capacitor and a resistor, or it will contain a reset IC available already in the market called Max 810. Fine. Select the reset IC based on the type of reset signal, logic level supported by the processor or the controller. So depending on whether it is CMOS level or TTL level, that is transistor level or CMOS level, or depending on whether it is active low or active high. Okay, so depending on all these parameters, we have to select the reset IC. Some processor or the controller contain a built-in internal reset circuit. They don't require any external reset circuit. So as I said earlier, so processors will have the reset circuitry on their chip. So sometimes it is not necessary to put any external reset circuit. So this is how the reset circuit looks. A resistor and the capacitor based on passive reset circuit for active high and low configuration. So one is for active high, one is for active low configuration. So here this is for active high and this is for active low pulse. So you can see here there is one capacitor, there is a resistor and a freewheeling diode which will support the current flow back to the capacitor. So initially, suppose when VCC is applied, the capacitor charges, so you will get a reactive high output. Then if it is low, the capacitor will discharge through the resistor. So while discharging, you will get the active low pulse. Okay, so this is how it will work. So reset pulse width can be adjusted by changing the value of resistance R and C. Okay, we'll stop here. In the next class, we'll continue with the brownout protection circuit. Thank you.